Let's talk about Green's theorem. So Green's theorem, on Monday we talked about the fundamental theorem of line integrals, and we found that for a conservative field, if we have a conservative vector field, then the line integral along that vector field was just the potential function evaluated at the endpoints, the difference in the potential functions evaluated at the endpoints. I posted yesterday, I posted my derivation of the conservation of energy, which relies on the fundamental theorem of line integrals. If we assume that Newton's laws are true, and we assume that we have a conservative field, electromagnetism is conservative, gravity is conservative, then we can derive the conservation of energy. I suggest you take a look at that derivation because it's kind of nice and it's pretty easy, and we have everything we need to understand it. Now, Green's theorem relates a line integral around a closed curve to the integral over the region enclosed by the curve. So again, we're talking about a boundary and a region. So we're talking about, if we're thinking like we did in Calc 1, where our region is between x1 and x2, and our boundaries are the 2 points x1 and x2. Green's theorem is kind of an extension of that. It's named for George Green. He was self-taught. He learned math from library books. He worked in his father's bakery, and he was one of the first people that tried to come up with a mathematical foundation for electromagnetism, and he influenced people who were working in physics on electromagnetism, including Maxwell, who's famous for his treatise on electromagnetism. So Green was one of the first people that tried to build a mathematical foundation for electromagnetism. So for Green's theorem, we need to talk about we need to define a couple of terms. For Green's theorem applies to what we call a simply connected region. So we need a few things for what we mean by a simply connected region. And we'll have several parts to this. So a simple curve doesn't intersect itself except at its endpoints. So we'll say it only intersects itself at its endpoints. And these terms will come up a lot when we talk about Green's theorem and as we go forward with what we're talking about in this chapter. A simple closed curve. Actually, I did this. This is too restrictive for a simple curve. A simple curve, let's see, this should be, a simple curve does not intersect itself anywhere between its endpoints. Sorry. A simple closed curve intersects itself only at its endpoints. And finally, a simply connected region. That's what we're trying to get to. A simply connected region is the boundary, is a region where the boundary consists of exactly one simple closed curve. And we'll draw some pictures here in just a second. So a simple closed curve, we have a curve that intersects itself only at its endpoints. A simply connected region is a region whose boundary is exactly one simple closed curve. And a simple curve doesn't intersect itself between its endpoints. So let's draw some pictures. This is simple. That's a simple curve. This curve is not simple. And that sound is very annoying. Soothing. This is simply connected. Or sorry, simply closed. Whoops. This curve is not simply closed. And this region is simply connected. And a region, something like this, would be an example of a not simply connected region, the region between these two curves. Simply closed is the curve. Simply connected is the region. So a curve is the boundary of the region. So for simply connected, we're talking about regions. All right. So for our curves, we're going to define the positive. Guys, listen up. We're going to define the orientation as counterclockwise. So that's going to be our positive orientation. For a curve, the positive orientation is counterclockwise. So when we're going around a curve, our positive orientation, we said when we parameterize a curve, the parameterization introduces an orientation. We're going to define the positive orientation as counterclockwise. So the region always remains on the left as the point traces the curve. That's going to be our positive orientation. So now we're ready to state Green's theorem. We're not going to prove it. The proof is kind of long, and we have to consider several different cases. We're going to state Green's theorem. So Green's theorem tells us that we have a piecewise smooth curve piecewise smooth and simple closed curve curve is C, and C bounds a region R in the plane. And this is an important piece. Green's theorem deals with plane curves. Additionally, we have m of x and y and n of x and y are continuous and have continuous first partials. So we have nicely behaved functions. All right, so our theorem. So these are our conditions. We have a piecewise smooth, simple closed curve. The closed curve bounds a region in the plane. We have these functions m and n that are continuous and have continuous first partials in our region. Green's theorem tells us the line integral around our curve, and this is our symbol. We get a new symbol now for a line integral around a curve, and the little arrow indicates the orientation. So we're going in the counterclockwise direction. The line integral of m dx plus n dy equals the double integral over our region of dn dx minus dm dy, those are partials, times dA. So this denotes the integral around our closed curve with positive orientation. And remember that m dx plus n dy, the other way we can write m dx, n dy, an equivalent expression is f dot dr, where f is mi plus nj. These two expressions mean the same thing. So what Green's theorem is telling us is that the double integral of this quantity of derivatives in this region equals the line integral of our functions on the boundary. So this is another kind of extension, another generalization of the fundamental theorem of calculus. Here we have a double integral of derivatives. Fundamental theorem of calculus says the integral of a derivative is just the function. So our functions are m and n, and we're evaluating those on the boundary of our region. So that's what Green's theorem is telling us. Now the reason we might use Green's theorem. Well, one, let's talk about a couple of things first. If f is continuous, or not continuous, if f is conservative, what is this quantity? If f is conservative, dn dx equals dm dy. So this is 0. So this tells us that if f is conservative, the line integral around this closed curve is 0. Now the reason we might use Green's theorem is sometimes the line integral might be difficult to evaluate. So then we evaluate the double integral over the double integral of this quantity over the region. If we have a double integral that we can express in this way, it might be easier to evaluate the double integral in terms of a line integral around the boundary. Just like sometimes it's easier to evaluate a line integral by using the fundamental theorem of line integrals, and evaluating your potential function at the endpoint and taking the difference. So let's look at a couple of examples using Green's theorem. Any questions before we go on? So I just want to emphasize Green's theorem, one of the major important theorems of chapter 15. And I know from last year on the UCD final, they had a problem where they didn't say use Green's theorem to evaluate, but they give you the conditions such that you could use Green's theorem. So it's important to recognize what conditions and what quantities allow you to use Green's theorem. All right, so let's look at some examples. We want to verify verify Green's theorem for the line integral around this closed curve, and our integral is x e to the y dx plus e to the x dy. And C is our curve, is the boundary of this region. Between y equals x and y equals x to the third in the first quadrant. Yeah, we're still in the plane here. So we're in the first quadrant. We're just in the first quadrant of the xy plane. Okay? So let's sketch our region and see what we're talking about. So here's our first quadrant. Here's y equals x, and y equals x to the third does something like this. So our region is this. I'm going to call this C1 and this C2. So we're evaluating our line integral around that boundary. That would be our line integral. So to do our line integral, we need to break it into two pieces. So along C1, I'm going to let x be the parameter. So we need to parameterize our curve. So along C1, dy, or I'm sorry, y equals x to the third. So dy equals 3x squared dx. And our integral comes out to be the integral from 0 to 1 of x e to the x to the third, this is y, dx, plus e to the x dy is 3x squared dx. And we want to evaluate that. This one is not an easy one, not necessarily an easy one to evaluate. I used my calculator, and this is approximately 2.936. So that's a line integral along C1. I parameterized C1, expressed m and n in terms of my parameter, and evaluated the integral. Now along C2, I'm going to let x be the parameter again. X goes from 0 to 1. So I'm sorry, from 1 to 0. I did that backwards. So I'm starting up here and going down here. So x varies from 1 to 0, and y equals x. So dy equals dx. And my integral is integral from 1 to 0 of x e to the x dx plus e to the x dx. And that evaluates to approximately negative 2.718. And the total equals 0.22. So that's our line integral around that closed path. Our line integral evaluates to 0.22. Now we want to verify. We have the conditions for Green's theorem. We have these functions. We have a simple closed curve. And our region is bounded by the simple closed curve. So now we're going to apply Green's theorem. So the double integral over R of the partial of n with respect to x minus a partial of m with respect to y, and I'm just go back here really quick. This is m, and this is n for our vector field. So this turns into, first I'm going to calculate my partial, sorry, dn dx is e to the x, and dm dy is x e to the y. So our integral for our double integral on our region, we have x varies from 0 to 1, y varies from x to the third to x. We have e to the x minus x e to the y. dy dx. And when I evaluate this out, this is not a particularly difficult one to evaluate by hand. When I evaluate that, I get that is approximately 0.22. So our line integral around our curve equals a double integral of this quantity over the region. Questions on that example? All right, let's look at an example where Green's theorem, using Green's theorem, is preferable to using a line integral. So we want to use Green's theorem in this example. We're going to evaluate the line integral of y minus x dx plus 2x minus y dy, and c is the boundary of the region inside y equals square root of 25 minus x squared, and outside y equals square root of 9 minus x squared. So like I suggested when we did double integrals, I always suggest when we're using Green's theorem, sketch your region. So let's sketch this. What's the region, what's inside the square root of 25 minus x squared? What is that? Circle. So we have a circle like so. And outside y equals 9 minus x squared, so we have another circle. Radius 3. So our region is going to look like, so we're here at 3 and 5. So there's our boundary. To do the line integral around that boundary, I would have to do 1, 2, 3, 4 line integrals. So that would be, it's doable. It would be a little tedious. And these paths with square root of 25 minus x squared and 9 minus x squared, we need to parameterize that. We need to express our functions in terms of the parameters. Those integrals could be extremely difficult to evaluate. So let's use Green's theorem. We have this function, m dx plus n dy. We have a simple closed curve bounding our region. So our region is in here. So m, in this case, is y minus x. So dm dy is 1. N in this case is 2x minus y. dn dx is 2. So we need to evaluate the double integral over our region of dn dx minus dm dy, 2 minus 1 dA, or, so what we're evaluating is the integral over our region of dA. What's a double integral of dA? If we're the double integral of just dA, what do we get? The area. The double integral of dA is just the area of the region. So do we even need to integrate to find that? No. The area is the area of the larger, we take the area of the larger circle, the larger half circle, subtract the area of the smaller half circle, and we have our answer. So this is just the area of R. The double integral of dA is just the area. And this equals 1/2 pi times 5 squared minus pi times 3 squared. And we get 8 pi. So we didn't even have to integrate. So this would be one example of when you would want to use Green's theorem to evaluate a line integral. So if you're evaluating a line integral, if you have a closed curve and you need to evaluate the line integral around that closed curve, so here's a second tip when we're looking at line integrals. The first tip is see if your vector field is conservative. If your vector field is conservative, you know that the integral around a closed curve is 0. If you don't have a closed curve, if your vector field is conservative, you know that you can evaluate the line integral along any simpler path between your endpoints, or you can find a potential function and evaluate the potential function at the endpoints and find the difference, and that'll give you your line integral. If we have a closed region and our field is not conservative, we can use Green's theorem to transform the line integral into a double integral over our region. And often that double integral on the region is easier to evaluate than multiple line integrals around the boundary. So let's look at one more example, and then we'll be done. So we want to evaluate this line integral of e to the x cosine 2y dx minus 2e to the x sine y dy. Or sorry, sine 2y dy. And c is the curve x squared plus y squared equals 9. Let's say, I'm not going to say a, I'm just going to say a squared. We're just going to give it a radius. So what this region is a circle with radius a. So what we're talking about is a line integral around this circle. This is my curve. And this is my region. So think about, look at this integral and think about how you would parameterize this curve. How would you go about parameterizing this curve? So x squared plus y squared equals a squared. So, right, we'd use cosines and sines. X equals r cosine theta, r equals, or y equals r sine theta. So we parameterize this curve in terms of r and theta. We express these quantities in terms of our parameters. So we have e raised to some trig function. We have the cosine of 2y, so we'd end up having to use trig identities to transform this quantity. We'd have to express dx in terms of our parameters to evaluate this line integral. So let's think about using Green's theorem here. Instead of trying to evaluate this line integral around the boundary, let's use Green's theorem. So dm dy is minus 2e to the x sine 2y. And again, this is m. And this is n. dn dx equals minus 2e to the x sine 2y. So, right, dn dx equals dm dy. So what is this line integral? Right. Our integral evaluates to 0. So if we tried to evaluate this line integral directly, it would be extremely difficult. So again, we go back to our tips for evaluating line integrals. See if f is conservative. It turns out in this case that f is conservative, so we know that the line integral around any closed path for that field is going to be 0. And if we didn't think in terms of a conservative field, if we thought, well, we have a line integral around a closed path, let's look at Green's theorem. We have to calculate these for Green's theorem, these partials for Green's theorem also, and we find that our line integral is 0. So Green's theorem can save us a tremendous amount of work in evaluating line integrals, because it very often is easier to evaluate the double integral over the region than it is to evaluate the line integral on the boundary. And I just want to emphasize again, this is another generalization of the fundamental theorem of calculus. We have the integral of some derivative quantity in a region being equivalent to those quantities evaluated on the boundary of the region. All right, questions? Homework. There you go.